Dear students, in the today's lecture, we are going to discuss the concept of oscillations, simple harmonic motion, definition, equation of motion, and its solution, and spring systems. To get the idea about concept of oscillation, we should know about periodic motion. What is periodic motion? A motion is said to be periodic if it repeats in the regular intervals of time. For example, a particle is moving along a circular path. If it repeats in this path in regular intervals of time, then we can say a periodic motion. For example, it completes one circular path in 2 seconds. So every 2 seconds, the motion is repeated. So it is a periodic motion. Similarly, we can discuss one more example. Here a particle is moving along a straight line path about a equilibrium position. So in this case, the particle is moving about a equilibrium position back and forth. This kind of periodic motion is known as oscillatory motion. So oscillatory motion is a periodic motion in which the particle is moving back and forth about the equilibrium position. So the time taken for completion of one revolution in this case, the time taken for completion of one oscillation in this case is known as time period. And number of revolutions per second in this case and number of oscillations per second in this case is known as frequency. So the time period and frequency are the two important parameters in the concept of periodic motion. If the frequency of these oscillations are high, these oscillations are named as vibrations. For example, the guitar string we can say vibrating, not oscillating. If frequency is low, that we named as oscillations. For example, a simple pendulum is oscillating. We can't say simple pendulum is vibrating. Now we are going to discuss the important motion in case of oscillatory in the nature that is always appears, that is simple harmonic motion. A oscillatory motion is said to be simple harmonic if it satisfies two conditions. Condition one is the acceleration or force always direct towards the mean position, that is equilibrium position. The second one is the acceleration or force directly proportional to the displacement. If you take a mass loaded spring here, if you see, it is oscillating on a frictionless surface here. So here, this is the mean position here, equilibrium position. When it is moving away from this equilibrium position, there is an elongation in the spring. That elongation makes the changes in the interatomic separation. That will develop some force in the spring and makes the object comes to the equilibrium position. Those forces are called restoring forces. So those restoring forces takes the object to the equilibrium position. When the object comes into the equilibrium position, because of inertia, there is a further compression in the spring that again develops the restoring forces and make it move away from the compressive position. So in this way, oscillations are set in the spring. In this case, if the object is moving away from the equilibrium position, the force acting on it always direct toward that equilibrium position. And also, the change in the force or acceleration depends on the displacement. For example, if you take this case here, so this is the equilibrium position here. From this equilibrium position, the object moves a distance of x. Then there is elongation in the spring. So some internal forces are developed in the spring because of interatomic separation changes. Then those forces takes the object to the actual position. But when the object coming to the actual position, the equilibrium position here, then because of inertia, it will move further. So there is a compression occurs in the spring. So because of this inertia and restoring forces, oscillations are set in the spring here. In this case, if you observe the first case here, the force is acting towards the equilibrium position here. And in this case also, the force is acting always towards the equilibrium position. And that force is directly proportional to the displacement x. So F is proportional to x. But it is opposite to the direction of force. That's why we can make it minus here. So F is proportional to minus x, or we can consider A also proportional to minus x, because we know according to Newton's second law, F equal to ma. So F is proportional to A. So if A is proportional to minus x, F also proportional to minus x. That proportionality replaced by constant K, known as restoring force constant. That is known as a restoring force constant. So this K is the restoring force constant here. Now we are going to write equation of motion of a simple harmonic oscillator. So now we discussed already, the force is directly proportional to the minus x, and proportional replaced by constant K, known as restoring force constant here, F equal to minus kx. But according to Newton's second law, we know F equal to ma. So A is the acceleration, that can be written as d square x by dt square, that equal to d square x by dt square. So this force is responsible to take the object to the actual position here. So both the forces are equal here. So by equating both the forces here, then we can get m into d square x by dt square equal to minus kx. So take this minus sign left side here and divide with m. So the resultant equation is d square x by dt square plus k by m into x. So this is the equation of motion of a simple harmonic oscillator. The solution of a simple harmonic equation of motion can be written as x equal to a sin omega t or x equal to a cos omega t. We can write, because the harmonic function is nothing but it is having either sine or cos terms here. So the harmonic oscillations, the phase variation is going along a sine or cos curve. That's why we can write the solution of a simple harmonic oscillator equation of motion as x equal to a sin omega t, or x equal to a cos omega t. Here a is the amplitude and omega is the angular frequency. So amplitude means the maximum displacement. So from this mean position here, how much distance it moves. So that is the amplitude here. Omega is the angular frequency. Now I differentiate this x value twice with respect to time. So x is the displacement at any instant. A is the maximum displacement, that is the amplitude. Now I differentiate this x with respect to time two times. So first time if you differentiate dx by dt equal to a cos omega t into omega. And second time if you differentiate that d square x by dt square equal to a sin omega t into omega square minus. So we know a sin omega t equal to x. So we can replace this a sin omega t with x. Then d square y by d square x by dt square equal to d square x by dt square equal to minus omega square x. So finally we can write the equation of motion as d square x by dt square equal to minus omega square x. Take this negative term left hand side. That equation becomes d square x by dt square plus omega square x equal to 0. So this is the equation of motion of a simple harmonic oscillator. Now we'll compare these two equations here. Then in place of k by m here, what we are having? Omega square. Therefore, omega square equal to k by m. So compare these two, then angular frequency equal to root k by m. So omega square equal to k by m. Therefore, angular frequency omega equal to root k by m. Now we are going to discuss the relation between this angular frequency and time period. So now angular frequency omega, time period t, and frequency f. How these three are related we will discuss now. We already showed the solution of a simple harmonic oscillator as x equal to a sine omega t. The solution of a simple harmonic motion equation of motion solution is x equal to a sine omega t. Now, if you add some value for this t, again we are getting the initial x value. Then how much we have added to this t, that is nothing but time period. So, for example, I am adding a value of 2 pi by omega t to this t here. Then what we will get here? A sine omega t into, so here if you go this omega inside and omega and this omega will cancel, 2 pi will remains. So what remains here now? X equal to a sine omega t plus 2 pi. That means sine 2 pi plus omega t. So sine 360 plus omega t. Sine 360 plus theta is the sine theta. So therefore, this value is again equal to a sine omega t. That means after 2 pi by omega seconds, it will come to the actual position again. That means it repeats its actual position after 2 pi by omega seconds. So that's why 2 pi by omega is the time period. Therefore, the time period t equal to 2 pi by omega. So from this, we already discussed here. So 2 omega equal to how much? 2 pi by t, and 1 by t is the frequency. So reciprocal of time period is the frequency. Therefore, omega equal to 2 pi by f. So in this way, omega relates with the frequency, and in this way, time period relates with the angular frequency. And we already proved omega equal to root k by m. So omega equal to root k by m is equal to 2 pi f. From this frequency f equal to how much? 1 by 2 pi root k by m. Frequency f equal to 1 by 2 pi root k by m. And if you want to find out the time period, it is a reciprocal of the frequency. So that equal to 2 pi into root m by k. So in this way, we can find the relation between omega, time period, and frequency. Now we are going to discuss spring systems. That is, two springs are connected in parallel as well as two springs which are connected in a series. Let us consider two springs which are connected parallel. These are two springs which are connected parallel. Now there is no load acting on it. Now we are applying some load on it. So then what happens here? Because of this force, there is some elongation here. This force is divided among these two springs, along the spring 1, F1, along spring 2, F2. And because of these forces, there is a elongation in the spring. That elongation may be X. Now in this case, the total force F equal to sum of the forces acting along the both the springs. That is F equal to F1 plus F2. We already discussed here F equal to minus Kx. Suppose the spring constant of the spring 1 is K1 for suppose, and spring 2, that spring constant is K2, then F1 equal to minus K1 into X, because the elongation in the both the springs is same, and F2 equal to minus K2 into X. F is the resultant force. The resultant force is related to the spring constant of this combination. If combination is parallel, so the resultant spring constant we can write it as a Kp or K parallel, then F equal to minus Kp into X. So therefore F equal to minus Kp into X. What is the Kp? Resultant force constant of a spring system which is having two springs in parallel, and F1 equal to minus K1 into X, and F2 equal to minus K2 into X. Therefore, F equal to F1 plus F2. So this implies minus Kp into X equal to minus K1 into X plus minus K2 into X. So we can take common on both sides and cancel. We can take minus also cancel both sides. Then finally we will get Kp equal to K1 plus K2. So if two springs are connected in parallel, the resultant force constant is equal to the sum of the force constants of the individual springs. For suppose both the springs are connected in a series. If the springs are connected in series, now a load we are applying. So then there is a force acting along the springs here. So there is a elongation in the both the springs here. And here we are assuming the mass of the spring is almost neglected. Now, how much elongation in the spring 1? There is a elongation of spring 1 this much here. So this much of elongation that we named as x1. Now coming to the elongation of second spring. So if you take the situation here, this x value will show the elongation of a total spring system in which two springs are connected in series. So this x is having the elongation of spring 1, that is x1, and also elongation of spring 2, that is x2. So that's why here this is x1. So what is the elongation we are getting in spring 1? And instead that one remaining portion, what is left over is, that is the x2. So in this case, the total elongation x equal to x1 plus x2. So in this case, total elongation x equal to x1 plus x2. We know f equal to minus kx, therefore x equal to minus f by k. So the spring constant of the first one is k1, and spring constant of second one is k2. Then x1 equal to minus f by k1, x2 equal to minus f by k2, because the force acting on both the springs is same. Then we will take the spring constant of total system as a ks, that is k series. Then x equal to how much? Minus f by k, minus f by ks. Therefore, minus f by ks is equal to minus f by k1 minus f by k2. In the both sides, we can take minus f common and cancel. Then 1 by ks equal to 1 by k1 plus 1 by k2. That ks is the resultant force constant when two springs are connected in a series. Then ks can be written as k1 k2 by k1 plus k2. In this way also we can write. In the next class, we are going to discuss about different cases of simple harmonic oscillations. Till that time, thank you for listening.